All right, everyone, welcome back to our Chapter 9 practice test, and we're going to take a look at questions 7, 8, and 9 here. For these questions, we're going to use Hopital's rule if necessary to find the limit of these functions. Right, functions. So let's take a look at this first one, sine of x over x cubed. It probably didn't escape your attention that this is a one-sided limit. We're taking a look at the limit as x approaches 0 from the right. But if the limit exists at all, then it has to be equal to that right limit. So what we're going to do is we're going to find the limit without regard to right or left. Because if that limit does exist, then that is going to be the right limit as well. I notice that the limit of the numerator and the denominator are both 0 as x approaches 0. So the limit of sine x over x cubed, well, that's equal to the derivative of the numerator divided by the derivative of the denominator. And we can only use Hopital's rule because we did already show that the limit of the numerator and the denominator are 0 over 0. And this gives me the limit as x approaches 0 of cosine x over 3x squared. Now, when I look at this one, this is no longer an indeterminate form because the numerator has a limit of 1. So now my analysis has to change because I can no longer use Hopital's rule. Since the numerator is approaching 1 and the denominator is approaching 0, we know that this is going to approach infinity either positive or negative, but we don't know which one it is. So now this is where we're going to take a look at the side information, because now we're going to take a look at from the right side. Now from the right side, cosine x is always greater than 0. And then from the right side, 3x squared is also going to be greater than 0. Since both of those are greater than 0, basically we get a positive number over a positive number, and that gives me positive infinity. So this limit goes to positive infinity. Now let's take a look at our next one. We've got the limit as x approaches 0 of 1 over x squared to the x power. And if we do this one, we've got, well, let's check. What is the limit as x approaches 0 of 1 over x squared? And just like the previous one, we've got a constant on the numerator and 0 on the denominator. So this is going to approach positive infinity as it would be because of the x squared. And so in essence, what we're looking at here is of the form infinity to the 0 power, which is a disguised indeterminate form. Maybe disguised is the wrong way to say this. We're going to turn this into an indeterminate form to help us find the limit. So we're going to start off by setting some dummy function y equal to 1 over x squared to the x power. Then we take the natural log of both sides, and we see that the natural log of y is equal to the natural log of 1 over x squared to the x power, which totally invites you to put that x in front of the natural log. So that is simplified to the natural log of y equals x multiplied by the natural log of 1 over x squared. But we want a ratio, so we're going to use properties of division to say that that is the same thing as the natural log of 1 over x squared divided by 1 over x. And then we're going to find the limit of the left and the right. Looking at the numerator, the limit as x approaches 0 of the natural log of 1 over x squared. Well, as x goes to 0, 1 over x squared goes to infinity. And of course, the natural log of a number that approaches infinity is also going to approach infinity. So the numerator approaches infinity, and we already said that the denominator is going to approach infinity. This should be one of those limits that you have to have down cold, constant over something that grows to something that goes to 0. That's going to be infinity. So we're looking at an indeterminate form. Hopital's rule says that if we have an indeterminate form, we can take the derivative of the numerator and the denominator, find the limit, and that will be the same as our original rational limit. Taking my derivatives, the natural log of 1 over x squared is 1 over 1 over x squared multiplied by the derivative of 1 over x squared, which is negative 2 over x cubed. And of course, the derivative of 1 over x, that's negative 1 over x squared. I think you're going to want to simplify this. Well, that numerator simplifies to negative 2 over x, and the denominator simplifies to negative 1 over x squared, which gives us a limit of negative 2 over x over negative 1 over x squared, which further simplifies to the limit of 2x, which is just 0. So this entire piece of work that we did simplifies into the limit as x approaches 0 of the natural log of y is equal to 0. Your next step here is to exponentiate. So the limit as x approaches 0 of e to the natural log of y is equal to just e to the 0. E and the natural log of y e and the natural log are inverse functions, so we just get y for e to the natural log of y. And if you remember way back at the beginning, we said that y was 1 over x squared to the x power, and e to the 0 is just equal to 1. So of course, the limit as x approaches 0 of 1 over x squared to the x power, that's just equal to 1. Now for the last problem, we've got the limit as t approaches 0 of 1 over sine t minus 1 over t. As t approaches 0, sine t approaches 0, so we're going to get a 1 over 0, which is, of course, some kind of positive or negative infinity. And the same thing over here, this is going to be some kind of an infinity, positive infinity, or negative infinity. So since the second part of this could be positive or negative infinity, depending on how we approach 0, we're going to need to do two one-sided limits and see if they agree. The first thing to do here is to turn this into a ratio, so we can use Hopital's rule. Infinity minus infinity is one of those disguised indeterminate forms. So with the common denominator, we see that the limit as t approaches 0 from the right, and I'm going to do one-sided limits here, we're going to get t minus sine t over t sine t. For the numerator, the limit as t approaches 0 of t minus sine t, that's 0 minus 0, or 1. Did I say 1? I meant 0. And then the limit as t approaches 0 from the right of the denominator, t sine t, that's also equals 0. So since the limits of the numerator and the denominator are equal to 0, this is an indeterminate form, and we can use Hopital's rule. So we're going to take the derivative of the numerator and the denominator separately. Our derivatives are 1 minus cosine t over sine t plus t cosine t. We'll check for indeterminate again. So the limit as t approaches 0 of 1 minus cosine t is 0. And then the derivative of, or as t approaches 0, sine t plus t sine t, that's also equal to 0. So we've got another indeterminate form. So we'll use Hopital's rule again. This time we get sine t over cosine t plus cosine t minus t sine t. As t approaches 0, sine t approaches 0 as well. But the limit as t approaches 0 of 2 cosine t minus t sine t, well, that's equal to 2. And note that it doesn't matter if we approach it from the left or the right, we still get the same results. So the left limit and the right limit agree with each other. And we can say that the limit as t approaches 0 without regard to sign restrictions, that's going to be the same thing. That's going to be equal to 0. So that's going to be all of the ones we go over today. Some pretty good Hopital rule problems for you, and we'll see you at the next video.